Okay, in this video, we're going to talk about queues. We normally would have had Monday or yesterday we would have had time there to talk about queues and do the queues on paper like we did on stacks. But due to the snow days, we just don't have the time. So we're going to have to move forward, which means tomorrow in class, we're going to be starting on programming on queues directly. So I've put the tutorial out there. Hopefully you'll read through that. And in this video, I'm going to go through the tutorial and kind of explain things in a little bit more because there's some oddities that come along with queues that we need to talk about. Okay. So first, let's talk about queues in general. Okay. Queues without any implementation. So unlike a stack, a queue is a first in, first out. Okay. So that's different from what we've done before. The functions we typically get on a queue are going to be enqueue and dequeue, enqueue, enqueue, see it on the paper here, or on the screen here, adds to the queue. It adds to the back of the queue. The dequeue removes from the front. So again, think that you're like in a line to see a show. Okay. The first person in line, uh, so you enter at the back. If you're the 10th person, then you will be at the end of the line behind the other nine people. Okay. But when it's time to let people in, the person in position number one would go in first and then two, and then you would be the 10th to go in. Okay. So that's the basic idea of this. So unlike a stack, which reverses everything with its first in, last out, a queue keeps things in the same order they were in. Okay. So in addition to the enqueue and dequeue, we typically have an is empty and we have an is full. Okay. And we have, I've got here as functions, and that's not correct. The front element will be an index between zero and the maximum size of the array, since if we're doing arrays, okay? And the rear element is also a position. So if we're talking about a linked list, it'll be a pointer. But if we're talking about an array, which we'll do first, it'll be an index position, okay? Just to let us know where things are, okay? So we have an is empty, is in full, and then we have a size, which lets us know how big things are. We often will also have like a utility function, like a print queue, okay? So there are lots of real world analogies when it comes to queues. Anytime you're in a line to do something, then you're in a queue. In fact, the British call a line a queue. They queue up to wait for something. Okay. Also, things if you're scheduling print jobs, ideally the first job to come in should be the first one that gets printed, right? Unless there are other priority factors. Same thing with CPU scheduling or a call center hold line. So calls should be taken in the order that they arrive. Okay. So again, the defining property of a queue that the first element added is the first one that gets removed. Okay. So again, if we would have had the time in class on Monday, we would have done some of these paper modeling activities. So we'll take a look at these as we go. Okay. So in the first case, we have some basic adds we're doing here. So we enqueue a 10. Again, this is the front. This is going to be defined as the front of the queue, and this is defined as the rear, at least direction wise. We add to this direction, we enqueue a 10. Okay, that's our content. So the front index is 0. We start off with the array-based ones with the rear being equal to -1. So in this case, the rear is 0 also. Okay. Then as we move forward and add a 20, then the front has a position of 1. We then add a 30. Again, I'm following a line, following along with this code over here. Okay. 30, our front, no, our front is still 0. That's incorrect. That's a 1, that's a 2. So now we're at 2 is the rear. And the count is now 3. Okay, we kept track of the count. Okay. So when we've done all of our additions from over here, the front's equal to 0, the rear is equal to 2, the count is equal to 3. Okay. So we now do a dequeue. When we do the dequeue, we remove from the front. Okay. So we're going to, because it's an array, we're going to just mark this one for deletion. Okay. And then what we're doing physically, we're moving the front to a 1. Okay. And the count will drop to a 2. We now do an enqueue on 40. That gets added at the end. Okay. and the rear is now a 3, and the count is now a 3. And then we do one more DQ, which is going to mark this one for deletion. And the front now goes to 2. The rear stays at 3. The count now drops back to 2. Okay. So that lets us know what happens in general. Okay, but we have a problem. Okay. We can go through this next example first. We haven't had a problem yet. We have a problem with arrays. We don't have a problem just on the screen. Okay. So here's an example through this program here. Our input, we're going to enqueue all, we're going to dequeue all. Okay, I'll go through it pretty quickly. We enqueue them all. They're going to look like this. Okay. At this point, the front is equal to 0. The rear is equal to 4. The count is equal to 5. Okay. As we dequeue the first one. So this one is going to get marked for deletion. Okay. That just moves the front up. It's now a 1, and it moves the count down 1. Okay. When we have deleted all of them, okay, the front then would be equal to 5. The rear would also be at 5, and the count would be 0. Okay. So again, we're assuming that there's no max size when we're just drawing them on paper. We can go as far as we want. Okay. So the next problem is a little more interesting. If we want to reverse the first kth elements, so let's say we're going to enqueue this time all the way to 6. So I'm going to go ahead and make all these back to being ready to go. Okay. So now we've enqueued 1, enqueue 2, all the way to enqueue 6. So at this point, our front is equal to 0, our rear is equal to 5, and our count is equal to 6. Okay. Our goal now is to take these first 3 elements. We're assuming that k is equal to 3. Again, we get that from the problem over here. K is equal to 3. Okay. We want to take the first 3 elements and reverse them. Okay. So to do this, and we get a hint here to use a stack temporarily. Okay, so I'm going to go ahead and make a vertical thing over here to represent our stack. Call this S1. Okay. So for each of these elements, okay, so we're going to do 3 times. If I delete items, so again, these are the 3 we're looking to do something with. Okay. If I dequeue them, okay, and push them onto the stack, when we're done with that, 1 goes in first, then 2, and then 3. As far as this goes, these are all now deleted from our stack. Okay. So we can now think about what to do with the rest of it. So we can't just enqueue them back in. If we just enqueued them back in, we'd end up with 3, 2, 1 over here, which is not what we want. Okay. So we're going to have another data structure that maintains this order. So we're just going to pop up another queue that's temporary. Okay. So I'm going to call this queue temp. Okay. I will then dequeue these 3 items one at a time. So this will go, the 4 goes to the front, then the 5, then the 6. Okay. So now we don't really mark these for deletion since it's an array, or since it's not an array. We're just dealing with the theory of it all. This would just look like this in our paper model. Okay. And we can reassemble this by starting from the stack. So if we here, that gets us that. Okay, we enqueue the top and then pop. we get there. If we NQ the top again, puts a 2 there, deletes it. One more time, we get to this. Now we're empty and we're done with this. Okay. Then we move to the Q temp, and if we DQ and NQ, okay, so basically we would say if our Q is called, let's just give this a name so that this will make some sense. We call this Q1. Okay. Then I would do a Q1 dot NQ Q temp dot DQ. Okay. So I would do this first, as long as this is not empty. Okay. Which will take this off of here, put it onto there, take this one off of here, put it onto there, take this one off of here, and put it on to there. Okay. And then the final version of this, these are both empty and can be deleted. Okay. Our front would now be 0, our rear would be 5, and our count would be back to 6. But we have the 3, 2, 1, 4, 5, 6, which is what was requested in the problem. Okay. So there are other examples here, but I think that's enough. You can work through those on your own. So let's now think about if we're going to model a queue with an array. And I'll revert this back as I'm talking. Okay. So in this case, to keep track of the front and the rear, we're going to use integers. Okay. And when we start off, when we initialize things, okay, I went too far. Let me go back here. We initialize things. We're going to initialize the front to be 0, but because on the rear, if we delete one, we basically need to move forward the rear the first time. So let's see why we're doing a 0 and a -1. If we add our first element here, okay, we want the front to be 0 and the rear to be 0. But since the rear has to move up 1, okay, we're going to put that as a 0. Sorry, as a -1 to make it a 0. Okay. That's how that's going to work. Okay. So on the queue here, we're checking for the full. We'll eventually put it in its full function. But if the rear is equal to max minus 1, so in this case, I should put this here as well, our max is equal to 10. It's an array, so we have to have a maximum size there. We will dynamically allocate this in our constructor, but once it's allocated, it is what it is. We set the max. Okay, so our max is 10. So we're full if the rear is equal to max minus 1. So if it's equal to 9, so where is full at rear equal to 9 in this example. Okay. If it's not full, then we're going to check to see if the front is equal to -1. Okay. If not, we're going to make it a 0 in case it goes off the edge somehow. And then we're going to increase the rear. Okay. And then, so from -1, we increase the rear to 0. Okay. So again, this stays where it's at. The rear is going to move to 0. Okay. And then we're going to place our value at that rear position since we add at the end. Okay. So we set the rear, place the value there. Okay. And this code doesn't say it, but then we would increase the count by 1. So now we're at 0, 0, and we have a count of 1. Okay. So in a DQ, if the front is equal to -1, okay, we know that we're empty, okay, or if the front is greater than the rear, which could happen, okay. When we start, the front is greater than the rear, the 0 and -1, okay. So if that's the case, then it's empty. We can't do anything. But if not, all we do to delete this is to move the front to one more. Okay, increase it by one. Okay, so that's the way the basic coding works on that. But we have a problem. Let's assume that, clear this out. Assume that we have this with only five. Okay, I want to do that. So in this case, our max is 5, and we are at full. Um, we'll worry about full. Full may change now. Okay. So if we insert a 10, a 20, a 30, a 40, and a 50. Okay. And then we DQ twice. So we're going to mark, so we're going to not really delete anything, but we're going to delete this one and we're going to delete this one. Okay. That puts our front at 2, our rear at 4. Okay. So we have space. So our count now is 3. If our count is 3 and our max is 5, we have room to do something here, right? We have room for 2 more. Okay. But we don't. If we try to insert something, okay, at the rear, we're going to add one to the rear, which gets us to 5 as the value. Okay. We try to insert at 5 and we can't. At least we shouldn't. I mean, C++ may let us, but it's going to be inconsistent. Okay. So we can't do that. So basically, it's called a deletion problem because when we delete, we are reducing the capacity by 1 every time. And if you have a gigantic array and you don't think that you're ever going to run out of space, then you could just let it slide, right? But that's not the best way to go about it. The best way to go about it is to be able to reuse these values. Okay. So if I would then add NQ a 60, it should be able to go right here, right? To use that space. Okay. And then it's valid, right? So in that case, our front would be equal to 2. Our rear would be equal to 0. And the count will be equal to 4. Okay. So this adds a bit of confusion to what we're doing. How do we get to that? So how do we get the rear to be equal to a 0 instead of a 5? And we do that with modulo math. Okay. So that's where we get this idea of a circular cube. So with that, we have 2 formulas we're going to deal with. We're going to say that the rear, we got to reset it to update it. Okay. Doing our modulo is going to be equal to rear plus 1. We're going to mod that on the max. Okay. So in the example that we just did, the rear is equal to the rear, which is 4, plus 1, which is 5, mod 5, which is going to set our rear to 0, which is what we want. Okay. Then when it comes to DQ, we could have the same issue coming back the other way. Okay. So with a DQ, we have to let the front, instead of just being front plus 1, we're going to let the front be equal to the front plus 1. Again, mod that with the max. Okay, the max is in all capital letters because it's going to be a constant. Okay. So that's how we're gonna do that. Okay. And then we have to worry about we're full if the rear plus 1 mod max is equal to the front, we're full. And then we're empty if either the front's equal to -1 or the front is equal to rear plus 1. Okay. So as far as the code goes, I have put some code out here for us to begin with. Okay. And it starts with the Q ADT. For the same reasons we did the ADT before, we're going to do one for Qs as well. Okay. Make this a little bit bigger for you. Hopefully. Okay. So for the Q's as well, we're going to make this QADT. Okay, exactly like we did before. In that it's in that we're going to have it so it defines the behavior, and then we're going to implement the Q's either with an array or a linked list, and our programs will not be affected. Okay, it's polymorphism in action. Okay, so we have our constructor. Okay, we have the destructor. Okay, actually, we don't have the constructor. The reason we don't have the constructor is on the linked list version, the constructor will have to set up pointers. On the array version, the constructor has to set the initial values of the front and rear pointers that are they're not pointers, front and rear index positions. So we can't put a parameter list in here in our function signature, or it wouldn't be correct for both. So we don't put it in there at all. But we do create the virtual constructor, okay, because it doesn't take any parameters. And then the things that are not going to change, we have the NQ, which takes an int value, the DQ. I'm going to call a peak front, peak rear, so we can see what's there. Okay, it returns the int. Then we have is empty, is full, and the size. And we're going to have a utility for display. Okay. So this peak front is sometimes just called front, but that's a little confusing. So I'm going to go with peak front this time. These are pure virtual functions, which means that anything that inherits from these functions are obligated to have these functions in these exact formats. Okay. Have to match the signature. Okay. So let's take a look now at the array q.h. This is going to include the ADT file, the qadt.h. Okay. It's then going to inherit publicly, the array q inherits from the qadt. Okay. Our constructor now takes an int for capacity. If we would have put that constructor as a virtual function in a pure virtual function in the ADT, we would have had to do this same thing for the linked list, and it doesn't make sense for the linked list to take a parameter like this because there's no capacity for a linked list except the size of the memory. Okay. So that's why we do this. We have our destructor again that comes through. All these functions come through as well. Okay. They're all the same, except that we're putting the override. Someone asked about override in class. The override is not mandatory. It will work without it. The override is just a clue to whoever's looking at this that this is from the parent class. Okay. So we see a value for it here. We know now that the constructor is not in the .h, not in the ADT. It's in the .h, but it's not in the QADT.h. Okay. It's not there. These other ones are. So it's easy to see what's what. Okay. And again, don't forget the constant if it's there, because if the .h file has a constant in it and your implementation of that does not, it will not match up and it will tell you it can't find the file, can't find the function. Okay. So here are the things that we're adding in particular for the array-based version. Okay. So we have our dynamic array. So we have our int star ARR for the array. Okay. We then have the indexes of the front and of the rear. We have also the capacity, and we have the current count. Those are all ints. Okay. So let's take a look then at the CPP file, which is what we'll be working on first. So as before, I've given you the constructor and the destructor just so we can see the players and what they're doing. Okay. And in this case, we don't have a max. We're just going to use the capacity instead, because it would be hard to make a global variable in this class structure with the array. Okay. So our constructor then that takes the capacity. I want to say capability every time. The capacity. Okay. It's going to set this capacity, which is the capacity of the array queue that is being created. Okay. And that's a pointer. So we have the arrow equal to the capacity that comes in. Okay. We don't have to pass it in as a different variable because we're using the pointer value on the left hand side, and because you just can't say capacity equals capacity, but that should work. Okay. The next line here, we're going to allocate memory to the array. So the array is already there as a dynamic array, the ARR, but it doesn't have any memory. We now have memory int based on the capacity. Okay. And I didn't say it, but it came up in the other problems. And we'll have to deal with this maybe before midterm, maybe not. We're making all of our data structures now for simplicity to be integer based. So one of the problems, one or two of the problems for the stacks needed a string stack. So I went ahead and created other versions. All I did was take the int version, wherever it said int, put a stack, pretty much. Okay. So we could do the same thing for queues. Okay. The real solution, which we'll get to, is to create a templated class where the type is passed in as a parameter. Okay, but I didn't want to add that complexity yet, but we'll get there. Okay, so just from our discussion before, we're going to set the front to 0, the rear to -1, and the count to 0 on our initialization. Okay, and then when it comes time for um, the the destructor, all we have to worry about is this array that we have created. Okay. So that's all we do there. We just delete that array. Again, the delete, someone had a question about that. We have to put in the brackets if we're deleting consecutive memory. Okay. Not 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 a single memory element. Okay. That's where that comes in. And then for the rest of the operations of the function, the rest of the functions of this, okay, I've given you the algorithms, basically what you need to do. Okay, so these should be relatively, it tells you pretty much what you need to do. I've given you pretty good instructions, I think, on these, including the formulas. Okay, so that may be more than you need, and it may be better not to do that, but I want to make sure we're understanding these. Okay, so you'll go through and create those first, and then again, the utility function we have is just going to print those out, okay, using that circular indexing. So important to keep that modulo function in there, okay? So that's the idea with queues, right? So hopefully you'll take a look at this, and then in class tomorrow, we will talk more about the queues and work on some programming examples. And hopefully we won't have any more snow days. We won't get any further behind.